If you really want to understand chemistry, I mean really get it, you have to learn how to speak the language of the atom. And guess what? That language is basically a secret code. It's written in something called quantum numbers. They are the key, the absolute blueprint for describing the weird, fuzzy, probabilistic world of the electron. And today, we are going to crack that code together. So, here's our game plan. First, we're going to figure out why we even need this crazy new system to find electrons. Then, we'll break down each of the 4 quantum numbers one by one. And finally, we'll put it all together to find the unique address for any electron you can think of.
All right, let's just dive right in. We have to start with a pretty big problem. The map of the atom you probably have in your head right now? Well, it's wrong. It's time to throw it out and draw a brand new one. Come on, we all have that picture in our minds, right? You've got the nucleus, that's the sun, and you have these little electron planets zipping around in perfect, neat little orbits. It's a nice, simple image, it's clean, but here's the thing. Quantum mechanics blew that idea completely out of the water. The reality is so much stranger and honestly, so much cooler.
This right here is such a perfect way to think about it. It gets to the heart of this huge idea in quantum mechanics called Heisenberg's uncertainty principle. Now, in simple terms, it just means you can't know an electron's exact position and its exact momentum at the same time. The more you know one, the less you know the other. So trying to pinpoint an electron is like trying to take a crystal clear photo of a single mosquito in a giant buzzing swarm. All you're ever going to get is a blur.
So, if we can't nail down exactly where an electron is, what the heck can we know? Well, we can describe its most likely location. And the absolute best way to think about this is like an address. The 4 quantum numbers work together to give every single electron in an atom its own unique address. And this address doesn't point to a spot. It describes a 3D region of space, called an orbital, where the electron is hanging out about 90% of the time.
Okay, let's start building that address, piece by piece. We'll begin with the biggest, most general part of the address, the state and the city. This is defined by the principal quantum number, which we just call n. So n is the big picture. It tells you the main energy level, or the shell, that the electron is in. This number is really the main thing that determines how much energy the electron has and, on average, how big its orbital is. The rules for n are super simple. It can be any positive whole number, 1, 2, 3, and so on. The bigger the number, the farther away the electron generally is from the nucleus, and, this is key, the more energy it has. That's why the electrons in the outermost shell, the ones with the highest n, are the ones that get involved in all the action of chemical reactions. They've got the most energy to play with.
Okay, so we've used n to find this city. Now we need to get more specific. We've got to find the right neighborhood. And that is the job of the azimuthal quantum number L. You see, while n gives you the overall energy level, L tells you the shape of the orbital inside that level. So you can think of these different shapes as different kinds of neighborhoods inside our city, each with its own unique layout and vibe. This is where it gets really visual. This table shows how the numbers for L translate into actual shapes. If L is 0, we get a perfectly spherical S subshell. If L equals 1, we get this cool dumbbell-shaped P subshell. And as L gets bigger, the shapes just get more and more complex and, well, beautiful. Now, this is so important to remember.
These shapes are not little racetracks that the electron follows. No. They are probability clouds. If you could take a snapshot of the electron's position 1 billion times, all those little dots would build up and create these exact shapes. It's the map of where the electron probably is.
So we've got the city and the neighborhood. Now we need the specific house on the street. That brings us to our third number, the magnetic quantum number, ML.
So what does this one do? Well, the magnetic quantum number, ML, tells us how that orbital shape is oriented in 3D space. I mean, think about it. A sphere can only point one way, right? It looks the same from all angles. But a dumbbell? That could be pointing up and down, side to side, or front to back. And there's a really simple rule that tells us how many orientations are possible. The value of ML can be any whole number from -L all the way up to +L, including 0. So for an S subshell where L is 0, ML can only be 0, one orientation, one orbital. But for a P subshell where L is 1, ML can be -1, 0, or +1. And that gives us 3 separate p orbitals, each pointing along a different axis, x, y, and z.
Okay, we've done it. We've found the house. Now for the very last piece of our address. There's a rule about who can live inside. And this is where the spin quantum number, ms, comes in. Now, this number is a little bit different from the others. It doesn't describe the orbital, the house, at all. It describes a property of the electron itself, something called spin. You can think of it like this. An orbital, our house, can hold a maximum of 2 electrons. They're like 2 roommates. And just like roommates, these 2 electrons have a very important rule they have to follow. They absolutely must have opposite spins. One is given the value of +1/2. We call that spin up, and the other gets -1/2, or spin down. When you have 2 electrons in the same orbital like this, we call them a spin pair. This whole idea leads us to one of the most important rules in all of science, the Pauli exclusion principle. Think of it as the ultimate law of quantum real estate. It says flat out that no 2 electrons in the same atom can have the exact same set of 4 quantum numbers. It's just not allowed. Even if they're in the same orbitals, sharing the same n, l, and ml, their spin numbers have to be different. This is what guarantees that every single electron has its own unique address. Okay, theory time is over. We've learned all the rules of this crazy address system. Now, let's actually put it to work. Let's find the complete address for an electron in a real-life element. The key to this whole thing? It's the periodic table. You know that giant chart on the wall of every chemistry classroom? It's not just a list of elements. It is a map of electron addresses. The row, or period, an element is in, that gives you N. The block it's in, S, P, D, or F, that gives you L. And its exact position inside that block helps you figure out ML and MS. It's all there. Let's try it for the very last electron added to a carbon atom. Okay, first find carbon on the table. You see it? It's in the second row, so N is 2. Easy. It's over on the right in the P block. That block corresponds to an L value of 1. Now, the P block has room for 3 orbitals, which we can label -1, 0, and +1. Carbon is the second element over in that block, so its last electron goes into the orbital we labeled ML equals 0. And finally, because it's in the first half of the electrons filling up that P block, its spin, MS, is +1/2. So the full address is 2, 1, 0 + 1/2. See? You just did it.
So, why does any of this matter? I mean, who cares? Well, this whole address system isn't just some neat filing system for electrons. It is the fundamental rulebook for all of chemistry. The specific order that these addresses get filled explains the entire structure of the periodic table. It explains why atoms form bonds the way they do, and ultimately it explains how all chemical reactions happen. It is literally the blueprint for all the matter we see around us.
And that just leaves us with this incredible mind-bending paradox, doesn't it? We have this beautiful, elegant, logical set of rules that governs everything with unbelievable precision. And yet, at its very core, what does the system describe? Not certainty. It describes probability, a cloud of maybes. So, the final question is just, what does it mean that our solid, tangible world is actually built on a foundation of pure, unadulterated uncertainty? That is something to think about.